Hey, hi everyone. Welcome to video on induction motor. In this video, we are going to see about the power and torque equation of induction motor. So let's begin with our learning outcomes. At the end of this session, the learner will be able to derive the power developed in the induction motor under standstill and running condition. They must be relate the rotor copper loss and rotor input. What is the rotor relationship between rotor copper loss and rotor input? Derive the equation of the torque developed inside the induction motor. These are the learning outcome for today's session. So before starting to the this session, let me introduce the equation about the three-phase power. In the three-phase circuit, we know that the three-phase power is given by two equation. One is root 3. Okay, so that is sqrt of 3 root 3 into vl il cos of phi. So this is the equation when we calculate the power in terms of line quantities. But if the power is to be calculated in terms of phase quantities, then this power equation will become 3 into VPH per phase power into IPH into cos of phi. So this will be the power when the quantities are in the line quantities. So phase quantities. So here we are knowing the per phase quantities. So let us develop the equation for rotor power in three phase circuit. So let's develop the equation for rotor power. Now we will first assume that rotor power in the three-phase circuit. In this, the rotor power is given at the standstill and under running condition. Under standstill condition, the EMF induced is a standstill EMF. 2 indicates rotor and 0 indicates standstill. So P2 means rotor power and 0 indicates standstill power is equal to 3. If we look into this equation, it is 3 E20 I20 into cos phi 20, where this E20 is our phase value of the rotor induced EMF, and this is also the phase value of the rotor EMF, and phi 20 is the our power factor in the at the standstill condition. So how will calculate the current? The current can be calculated as induced EMF the rotor in per phase. So what is the induced EMF in the rotor per phase? It is equal to E20. So induced EMF in the rotor is equal to E20. So this is the E20 divided by Z20. So what is Z20? Z20 is the impedance of the rotor per phase. So E20 upon R20. How will calculate the Z20? So what is the value of Z20? Impedance is equal to under root resistance square plus inductance square. So what is the resistance of the rotor? Rotor is resistance is R20. 0 indicates standstill. Okay, and X20 is the rotor resistance under standstill condition per phase. So E20 upon under root R20 square plus X20 square. So it is R plus J2 is equal to R plus JXL. I am considering only magnitude over here because I want the magnitude of the current here. So cos phi 20 is how we'll calculate the power factor. If we draw the power triangle diagram, so in the power triangle diagram, if this value is equal to P, this value is equal to Q, and this value is equal to S. Okay, similarly when you draw it resistance, then it is R, then this will be replaced by XL, and this will be replaced by impedance Z. So this is our power triangle diagram. So this power triangle diagram indicates that this is the power factor angle, this is my phi. So phi is to be calculated. So cos phi is what? R divided by Z. So that is R20 divided by Z20. So that is standstill resistance upon standstill impedance. So R20 upon Z20 is already calculated. It is R20 square plus X20 square. Okay, substituting this value into this power equation, substituting I20 and cos phi 20, I20 is equal to E20 upon Z20 and cos phi 20 is equal to R20 upon Z20. So what will become? E20 into E20 will become E20 square into R20 upon Z20 square is equal to 3 into E20 square R20 divided by Z square is equal to R20 square plus X20 square. So this is the equation of power in the induction motor under standstill condition. So what will happen in the running condition, that we will check. Under the running condition, so if we want to calculate the power under running condition, what is going to happen, that we will check. In the under running condition, if we look here, see that here it is a P20. I am replacing this P20 by P2R. So P2R, R indicates the running condition and P2 indicates the rotor power. So it is 3E2R. As it is a P2R, it must be E2R into I2R into cos phi 2R. So I will calculate I2R. For I2R, I have to take the EMF induced in the rotor per phase under running condition. Similarly, impedance of the rotor under running condition, since it is E20 upon Z20. See, in this diagram, it is E20 upon Z20. Now here it is E2R upon Z2R. So how will calculate E2R? What is the relationship of E2R with S2R? In the last video, we see that E2R is equal to S times E20. It is slip into E20. So Z2R, but under running condition, the resistance. So what is about the resistance? R20 is always equal to R2R. That is, under standstill and under running condition, resistance is not changing because resistance is not depending upon frequency, but reactance is S times of X20. This X2R, this will be X2, it is reactance is S times of X20. Similarly, we will calculate the power factor. So power factor is again R by Z, that is a cos phi 2R, hence it is R2R divided by Z2R. So it gives me R20 upon under root R20 square plus S into X20 square. If we calculate this, if we substitute this value into the power equation, 3E2R into I2R plus cos phi 2R, substituting the I2R from this equation and substituting phi 2R from this equation, I will get the value 3 S into E20 square R20 upon R20 square plus X20 square. So see that what is the change? Here it is X20, here it is the S into X20. Here it is E20, here it is S into E20 square. It indicates that standstill power is not depending upon the slip, but under running condition the power is depending upon the slip. So let's see the another. Let's see that is the develop. But how we'll calculate the power loss? Power loss under running condition is equal to 3I2R square into R20. It must be R2R, but R2R is equal to R20. Hence, it is power loss inside the induction machine in the rotor. Power loss in the rotor, I am talking about the copper loss. I am not talking about the iron loss. So, copper loss inside the rotor is given by 3I2R square into R20. So, let's calculate the torque developed relationship between rotor copper loss and rotor input. So what is the relationship between this copper loss and rotor input? From the input power, how much will be the copper loss? That we will calculate. Let us consider that tau d is the developed torque. Tau d, or you can say Td, is the developed torque in the rotor. Ns is the synchronous speed in RPS, as it is written as a small ns. So you can observe that this is written as a small ns over. So this small ns indicates that it is the speed is in RPS. If it is a capital Ns, then it is in RPM. Then here it is NR. NR is the rotor speed in RPS. Again, it is not in RPM, it is in RPS. Why I am taking into RPS? Because I want to calculate the omega. So that will become easy. So the power developed, always we know that how we will calculate the power. The power is always related by omega into torque. So omega into torque is always my power. So to calculate this omega into torque, I have to calculate the omega. What is air gap power? As the power is in air gap, who is feeding the power to the air gap? Stator is feeding. Hence, I have to take the omega s here, and this is nothing but the developed torque. Omega s into developed torque. So how will calculate omega? So we know that omega is equal to 2 pi into speed in RPS. So 2 pi, what is the speed? 2 pi n. N is the speed in RPS. If it is s, I have to take here s again. Okay. So that is replaced here. It is a 2 pi it is evaporated 2 pi ns into tau d. Similarly, mechanical power developed by the rotor, this is received by the stator. Now what is the rotor? Rotor is moving with the speed of omega r. As the rotor is moving with the speed of omega r, so what is the value of omega r? Omega r is equal to 2 pi nr. So the rotor power, so I will say the mechanical power developed inside the rotor is, again, power is always equal to omega into tau d. Okay, so omega into tau d, but here it is the rotor power, hence I have to take it as omega r. So omega r into tau d, so it gives me 2 pi nr into tau d. So by this way I can calculate the mechanical power developed by the rotor. In the rotor, power loss, we just saw in the previous slide that power loss is equal to 3 I2R square into R20. So how will this power loss is always nothing but what? PG minus PMD. That is stator is giving the output and rotor is producing the output. In between there is a rotor copper loss. So that rotor copper loss is PG minus PMD. So I will make this 18, equation number 18 minus equation number 19. So I will get 2 pi TD NS minus NR. So we will take the ratio of rotor copper loss divided by input power to the rotor. Rotor copper loss is equal to 2 pi D NS minus NR divided by 2 pi NS into tau d. So 2 pi tau d will get cancelled. It is ns minus nr into ns is equal to s. So it indicates that rotor copper loss is equal to s times of input power to the rotor. Means it is depending upon the slip. So you will observe that it is depending upon slip. So slip times rotor input. If the slip is larger, power loss inside the machine will be larger. Now let us develop. Okay, so now let us develop the equation for. Okay, so let us develop the equation for. Okay, so let us develop the equation for. Okay, so now let us develop the equation for torque equation inside the machine. So to calculate the torque equation inside the machine, okay, so to calculate this torque equation inside the machine, we require power. So we related this PG, okay, P2R or PG is calculated. So P2R is equal to 3 into S into 0 square R20 upon R20 square into S into X20. So input power to the rotor is nothing but 2 pi ns into tau d. That is the input power to the rotor we see in the earlier slide, and the rotor copper loss is equal to S times of the input power to the rotor. Now let us develop the equation for torque. So P2R is equal to the mechanical power developed. So P2R is equal to P2R is equal to PG. So substituting P2R is equal to PG on this side. So how will get the developed torque? I have to transfer this 2 pi ns term on this side. So S upon 2 pi ns is transferred. So this S and one of the S will be cancelled from the numerator. So I will make the constant term at one side. So 3 divided by 2 pi. I will take this term as a constant, 3 pi divided by 2 pi ns, because synchronous speed, once the machine is designed, the synchronous speed is going to remain constant. So taking this 3 pi upon 2 ns as a constant term, what will remain? S into E2R0 square R20 upon R20 square plus S into X20 square. So this where the K is replaced by K is nothing but 3 divided by 2 pi ns. So this is the torque developed inside the induction motor. Thank you. So in the next lecture we will see the maximum torque and the starting torque of the induction machine. Thank you.